Do you like to see things fly fast? Do you like to see things fly at a super high elevation? Then do we have a project for you.
I would like to talk to you about the importance of our project. Last year, the OSU student group of the American Institute of Aeronautics and Astronautics, or the OSU AIAA, started a team for a hybrid rocket motor in which they would use a mixture of fuels for the motor combustion chamber. Last year and several times this year, the motor did a catastrophe at takeoff, in other words, a CATO, in which the motor blew up. And that is why our project is very important. Our project consists of several sensors that are placed in various locations on the motor cylinder, and we log data of different types, and this will ensure that the team can use an optimized amount of hybrid chemicals so that they can get the motor to go as high up into the air by making it as combustible as possible without blowing up the motor again.
For the project overview, our hybrid rocket motor data logging system has 4 different types of sensors that it uses to log data. The 4 different types is load cell, thermocouple, pressure sensor, and we use a strain gauge as well. All of these 4 sensors have a voltage output that we use a LabVIEW executable to log all this data and store it onto a file on the computer. A few of the features that a system offers is a durable enclosure, 2 NI USB 6009 DAC devices to read in all the sensor signals. We also have a 10 volt and a 28 volt power supply which will be powering the circuits and all these sensors. We also have a main on and off switch for the whole system as an emergency shut-off switch, and we also have 16 Deutsch connectors which each have a unique switch with LEDs that indicate when the power is being supplied to the sensors. And we also have LabVIEW executable code that will be used as a graphical display code and display all the signals that are coming in, as well as save all the signals into a file on the computer which can be viewed and studied at a later time.
System overview. Our system is divided into 11 blocks, 6 of which were developed by us. And those are thermocouple sensor, strain gauge sensor, load cell sensor, enclosure, data logging code, and graphical user interface code. The remaining 5 blocks are power supply, load cell sensor, data processor 1, and data processor 2. Some of the technical challenges that we faced with the thermocouple sensor were that the output of the thermocouple sensor was in millivolts, which was too small for the DAC to read. So we developed an amplifier circuit to step up the voltage readings up to a level that's readable by the DAC. With the strain gauge sensor, the output of the signal was in ohms, and the DAC can only read volts. So in efforts of fixing that issue, an amplifier circuit was developed using a Wheatstone bridge. With the load cell sensor, we were facing difficulties trying to analyze the output ranges. So in efforts of figuring out a solution, we called the manufacturer and they guided us on how to properly test out the sensor output ranges. And we did that by using the hydraulic press. Enclosure. We used SolidWorks to design the enclosure in efforts of getting it 3D printed. But the enclosure ended up being too big to be printed. We tried partitioning it into smaller portions to fit the printing scale, but even with that, the enclosure did not meet our expectations. So we ended up buying a relay box and cutting the holes into it to the best of our abilities to make it look as close as possible to the anticipated enclosure we had in mind. Data logging code. After finishing up the coding and while testing out the code, we ran into the issue of the program collapsing after approximately a minute of running. After thorough analysis, we found out that the format that we're saving the data logs in was After doing a thorough analysis, we found out that the format that we're saving the logs in was the main reason that was causing the application to collapse. What we had to do to fix that problem was to change the format from an Excel to a text file. Graphical user interface. The graph obtained were too distorted, but after using an averaging filter within LabVIEW, we were able to obtain a cleaner signal output that helped us obtain a better looking graphs that did not look as distorted as before.
Now, I would like to lead you on an exploration of our project and give you an actual hands-on demo. Looking at the back of the enclosure, there is a main switch for the overall power. It is used in case of emergency, and then it can be switched off. In addition to this main switch, each sensor has its own switch for the power LED and a power LED indicator light. Any combination of sensors can be powered at any time. Our project can read in sensor data from any and all sensors at the same time. It is important that the presence or absence of sensors does not mess up the system. For the pressure transducer, we used a grease gun with a gauge to apply a pressure up to 1000 psi. The dial went up close to 1000, and the graphical interface on the computer showed close to 1000 as well. For the load cell, a hydraulic press was used to create 1000 pounds of force on the load cell. The indicator dial showed the value, and the correct value was outputted on the graphical interface. The thermocouple used a flame torch to heat a piece of metal shrapnel to high temperatures, and then the thin rod of the sensor touched the metal. The strain gauge was mounted to a PVC pipe, and 10 pounds of force was applied to the pipe. Certain equations were used to indicate that 10 pounds induced 0.00202 millimeter per millimeter of strain, and the voltage was outputted on the graphical interface. In addition to these tests, which were used to prove the system requirements and the extent of their abilities, these sensors were deployed in the various test fires that the hybrid rocket team had put on. The load cell was mounted right behind the motor cylinder. The pressure transducers were connected to the piping on the front and back of the motor cylinder, and the strain gauges will be mounted to the final motor cylinder in the future. Thermocouples were not used in the test fires, but will be used in the future. A cantilever load cell was used on the manifold stand to measure the load for that, as we were loading the rocket motor with the hybrid chemicals. The graphical interface simultaneously displays all sensor readings on the screen and will save the data to a file. It is able to turn on and off DAC1 and DAC2, so you can use either one or both at any given time.
For the timeline of our project, during fall term, we worked on analyzing what our system is going to be doing and what's the best solutions for it. When we were exploring our options for which devices to use to log data, we looked into using the Intel Edison board, using the National Instrument USB 6009 DAC device, and we're using the Rio device which the mechanical engineers provided to us. After doing much testing and analysis, we were able to figure out that the Rio DAC device wasn't working properly, and that the Intel Edison board was not preferred by the mechanical engineers because they really wanted us to use LabVIEW, and the only device that was compatible with LabVIEW was the USB 6009 DAC device. After doing much research and analysis and calling National Instruments, we were able to figure out how to use this DAC device and apply it with LabVIEW. Also, during fall term, each of us chose to do a sensor block, and we had to make sure that we had that block working properly for the checkoff. With the interface requirements we had, we did our test and proved that the sensors were working properly as specified. During winter term, we were dividing the remaining blocks of our system to each other and making sure that we have the whole system working for the final checkoff during that term. Each team member had to complete every single block that they were assigned by week 6 in order to pass the system. With multiple meetings every week and just having a lot of discussions with the mechanical engineers, we were able to analyze the system and fully understand what the requirements were of us, and so then we could actually make the system work towards those requirements and analyze the whole system and have the right and proper readings of each sensor. Also, the periodic test fires that we had every week were really helpful in analyzing our system and making sure that the code was working, and also analyzing that the sensors were outputting the right data for us and that we were able to log that data onto a file on the computer. During spring term, the whole system had to be completed and fully functional by week 7. With all the test fires that were going on, we were able to analyze our data and see that we were getting the results that we desired. We also used other ways and systems to test our sensors to make sure we meet the full limits of what was required by the stakeholder.
Lessons learned. This project taught us to never leave things till the last minute. It was also challenging to set up a time that works for the whole group to meet up, so we had our meetings decided on in advance. We also learned that there's a lot involved in working on a project with multiple groups from multiple disciplinaries. It also taught us that if one group does not meet the timeline, it not only affected them, but rather affected all other groups combined. Designing and printing our own printed circuit boards helped in designing circuits that would fit our needs better than just buying one. Lastly, we learned that we can't always expect things to work out the way we plan on, so we needed to always do multiple adjustments when needed.